NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve for the x-intercepts of the quadratic function f of x equals x squared plus 4x plus 3. We will follow a clear two-step process. First, we compute the discriminant. Second, we apply the quadratic formula. Finally, we will verify our answers on the graph. Let us draw a quick graph to build intuition. Here is a coordinate plane, and the parabola for f of x equals x squared plus 4x plus 3. We expect two intercepts because this quadratic factors nicely. We will confirm them algebraically next. Step 1. Compute the discriminant. 4ax squared plus bx plus c equals 0. The discriminant delta equals b squared minus 4ac. Here it equals 1, b equals 4, and c equals 3. So delta equals 16 minus 12 equals 4. Step 2. Apply the quadratic formula. X equals negative b plus or minus the square root of delta all over 2a. We substitute b equals 4, delta equals 4, and it equals 1. That gives x equals negative 4 plus or minus 2 over 2. The two solutions are x equals negative 3 and x equals negative 1. Now, let us show these solutions on the graph. We mark the points negative 3, 0 and negative 1, 0 on the x-axis. These are exactly the x-intercepts where f of x equals 0. Notice how they match the algebraic solutions perfectly. As a quick check, the quadratic factors as x plus 1 times x plus 3 equals 0, leading immediately to x equals negative 1 and x equals negative 3. We have solved the quadratic, and we confirmed the answers on the graph. Great work! You computed the discriminant, applied the quadratic formula, and interpreted the solutions on the graph. This workflow will serve you well for any quadratic function. In this video, we will find the zeros of the quadratic function f of x equals x squared plus x minus 6. We'll follow the simple algorithm. Set the function equal to 0, factor, and then solve each factor. Step 1. Set f of x equal to 0. That gives us the equation x squared plus x minus 6 equals 0. Step 2. Factor the quadratic. We need two numbers that multiply to negative 6 and add to positive 1. The pair plus 3 and minus 2 works. So we factor as open parenthesis x plus 3 close parenthesis times open parenthesis x minus 2 close parenthesis equals 0. Step 3. Use the zero product property. If a product equals 0, at least one factor equals 0. So set x plus 3 equal to 0 or x minus 2 equal to 0. That gives x equals negative 3 and x equals 2. Let's verify visually on the graph. We'll draw the x-axis and y-axis and plot the function x squared plus x minus 6. Notice where it crosses the horizontal axis. It crosses at x equals negative 3 and x equals 2, exactly our solutions. Quick check, plug in x equals negative 3. Negative 3 squared plus negative 3 minus 6 is 9 minus 3 minus 6 equals 0. Now plug in x equals 2. 2 squared plus 2 minus 6 is 4 plus 2 minus 6 equals 0. So, the zeros of the function are x equals negative 3 and x equals 2. These are exactly the x-intercepts where the graph touches the horizontal axis. In this example, we'll find the zeros of the function f of x equals x cubed minus 4x. We'll follow a clean four-step process. Set the function to 0, substitute, factor, and then solve. Step 1. To find where the function crosses the x-axis, set f of x equal to 0. Step 2. Substitute the expression for f of x. We replace f of x with x cubed minus 4x. Step 3. Factor out the greatest common factor. Both terms have x, so we pull out 1x. Then recognize a difference of squares x squared minus 4 equals x minus 2 times x plus 2. Step 4. Use the zero product property. If a product equals 0, then at least one factor must be 0. First factor x equals 0. Second factor x minus 2 equals 0 gives x equals 2. Third factor x plus 2 equals 0 gives x equals negative 2. So the zeros are x equals negative 2, 0, and 2. Let's visually check our answers on a graph. We draw axes, and the curve of x cubed minus 4x. Notice the graph crosses the x-axis at -2, 0, and 2. We'll mark these intercepts clearly. Recap. We set f of x to 0, substituted x cubed minus 4x, factored to x times x minus 2 times x plus 2, and applied the zero product property to get the three roots. In this example, we will find the real zeros, also called the roots of the function f of x equals 2x cubed plus x squared plus 3x. First, we will lay out the problem clearly, then follow a simple three-step algorithm. Step 1. Set the function equal to 0. This is how we start finding roots. We write f of x equals 0, which means 2x cubed plus x squared plus 3x equals 0. Step 2. Factor out the greatest common factor. Every term has an x, so factor out x. This gives x times, open parenthesis, 2x squared plus x plus 3, close parenthesis, equals 0. Step 3. Use the zero product property. If a product is 0, at least one factor is 0. So we split into two equations x equals 0, or 2x squared plus x plus 3 equals 0. To check the quadratic for real solutions, we use the discriminant delta equals b squared minus 4ac. Here it equals 2, b equals 1, c equals 3. Delta equals 1 squared minus 4 times 2 times 3, which is 1 minus 24, equals negative 23. Because delta is negative, the quadratic has no real roots. Therefore, the only real zero is x equals 0. Let's highlight our final answer and visualize why it makes sense. In this example, we will find the zeros of the function h of x equals x to the fourth plus 3x squared plus 5, following a clear step-by-step algorithm. Step 1. Set the function equal to 0. We write h of x equals 0, which means x to the fourth plus 3x squared plus 5 equals 0. Step 2. Use substitution. Because this is a biquadratic equation, we let x squared equal t. Then x to the fourth becomes t squared, and our equation becomes t squared plus 3t plus 5 equals 0. Step 3. Calculate the discriminant. For a t quadratic of the form a t squared plus bt plus c, the discriminant delta equals b squared minus 4ac. Here it equals 1, b equals 3, and c equals 5. So delta equals 3 squared minus 4 times 1 times 5, which is 9 minus 20, equal to negative 11. Step 4. Interpret the result. A negative discriminant means the quadratic in t has no real solutions. Since t equals x squared cannot be any of those non-real values, there are no real x that satisfy the original equation. Therefore, the function has no real zeros. Example. We will find the zeros of the function f of x equals open parenthesis x squared minus 1 close parenthesis squared plus open parenthesis x squared minus 1 close parenthesis minus 2. We'll follow a clean four-step algorithm. Step 1. Variable substitution. We notice the repeated expression x squared minus 1. Using substitution, we'll simplify the algebra dramatically. Let t equal x squared minus 1. Step 2. Form the quadratic in t. To find zeros, set f of x equal to 0. Then substitute t for x squared minus 1. This yields t squared plus t minus 2 equals 0. Step 3. Factor and solve in t. We want two numbers that multiply to negative 2 and add to positive 1. That is plus 2 and minus 1. So the factorization is open parenthesis t plus 2 close parenthesis times open parenthesis t minus 1 close parenthesis equals 0. Therefore, t equals negative 2 or t equals 1. Step 4. Back substitution to x. For t equals negative 2, x squared minus 1 equals negative 2. So x squared equals negative 1, which has no real solution. For t equals 1, x squared minus 1 equals 1, so x squared equals 2. Taking square roots gives x equals plus or minus square root of 2. Example. In this example, we will find the zeros of the function. F of x equals x to the fourth minus 10x squared plus 16. We will solve it step by step following a clear algorithm. Step 1. Set the function equal to 0. So, f of x equals 0. That gives us x to the fourth minus 10x squared plus 16 equals 0. Quick challenge. What substitution would make this look quadratic? Step 2. Substitution. Let x squared equal t. Then x to the fourth becomes t squared. Substituting, we get t squared minus 10t plus 16 equals 0, together with x squared equals t. Notice the new variable t replaces x squared everywhere. Step 3. Factor the quadratic. We seek two numbers that multiply to plus 16 and add to negative 10. Those are negative 8 and negative 2. So the factorization is t minus 8 times t minus 2 equals 0. Step 4. Solve for t and then for x. From t minus 8 equals 0, we get t equals 8. So x squared equals 8, and x equals plus or minus square root of 8. From t minus 2 equals 0, we get t equals 2, so x squared equals 2, and x equals plus or minus square root of 2. Final answer. The zeros are plus or minus square root of 8, and plus or minus square root of 2. Example, we will find the real zeros of the function g of x. The function is g of x equals the quantity x plus 1 over x squared, plus the quantity x plus 1 over x. Our plan will exactly follow a simple algorithm. Substitution. Solve in the new variable, then back substitute, and check each case. Step 1. Define the function and use substitution. Let y equal x plus 1 over x. Then set g of x equal to 0. Substituting y gives a simpler equation in y. Step 2. Set the function to 0 and solve for y. Factor out y. Y times y plus 1 equals 0. So we get two possibilities, y equals 0 or y equals negative 1. Now, we back substitute and solve each case. On the left, case 1, y equals 0. On the right, case 2, y equals negative 1. Case 1, y equals 0 means x plus 1 over x equals 0. Multiples 0. Multiply both sides by x to avoid fractions. We get x squared plus 1 equals 0. This has no real solutions because a square cannot be negative. Case 2, y equals negative 1 means x plus 1 over x equals negative 1. Multiply both sides by x. X squared plus 1 equals negative x, which rearranges to x squared plus x plus 1 equals 0. Use the discriminant b squared minus 4 ac. It is 1 minus 4 equals negative 3. So there are no real solutions in this case as well. Final conclusion. Neither case produced a real x value. Therefore, g of x has no real zeros. Only complex roots exist for this equation. In this lesson, we will find all zeros of a fifth-degree polynomial step by step and connect the algebra to a clear visual understanding of multiplicity and X-intercept behavior. Here are 3 essential facts about polynomial zeros that we will use. 1. An nth-degree polynomial has exactly n zeros, counting multiplicity. 2. If it is a zero of the polynomial, then x minus a is a factor. 3. If x minus a is a factor, then it is a zero of the polynomial. Here is the exercise. Find all zeros of the function p of x equals 5x to the 5 minus 20x to the 4 plus 5x cubed plus 50x squared minus 20x minus 40. Step 1. We use the given factorization. The polynomial can be written as 5 times x plus 1 squared times x minus 2 cubed. We will not derive this factorization now. We will use it to find the zeros and their multiplicities. Step 2. Set each factor equal to 0. From x plus 1 squared equals 0, we get x equals negative 1. The exponent 2 means this is a double root, multiplicity 2. From x minus 2 cubed equals 0, we get x equals 2. The exponent 3 means this is a triple root, multiplicity 3. Let us visualize multiplicity on a number line. A double root typically touches the axis and bounces. A triple root crosses the axis with a flattened, S-shaped crossing. Finally, check that multiplicities add up to the degree 5. 2 plus 3 equals 5. That matches the degree of the polynomial. Everything is consistent. Final answer. The zeros are x equals negative 1 with multiplicity 2 and x equals 2 with multiplicity 3. In this lesson, we will find the zeros, also called roots, of a polynomial using clean factoring and the zero product property. Step 1. Identify the function. We will work with the exact expression as given. Then we will factor it step by step. Step 2. Factor. First, pull out the greatest common power of x. which is x to the 4. That leaves a quartic in parentheses. Next, we use the factorization provided. The quartic equals left parenthesis x minus 3 right parenthesis cubed times left parenthesis x plus 5 right parenthesis. Let's quickly verify by expanding. First, x minus 3 cubed equals x cubed minus 9x squared plus 27x minus 27. Now multiply that by x plus 5. Multiply by x, then add 5 times the polynomial and combine like terms. We get x to the 4 minus 4x cubed minus 18x squared plus 108x minus 135, which matches our quartic. Therefore, the fully factored form is q of x equals x to the 4 times left parenthesis x minus 3 right parenthesis cubed times left parenthesis x plus 5 right parenthesis. Step 3. Step 3. Find zeros by setting q of x equal to 0 and using the zero product property. A product equals 0 only if at least one factor equals 0. So we solve x to the 4 equals 0, x minus 3 equals 0, and x plus 5 equals 0. This gives x equals 0 with multiplicity 4, x equals 3 with multiplicity 3, and x equals negative 5 with multiplicity 1. For a visual check, let us sketch the graph and look near each root. Odd multiplicity roots typically cross the horizontal axis, while even multiplicity roots typically touch and bounce. In this lesson, we will find the zeros of a 7th degree polynomial. Example, we are given r of x equals x to the 7th plus 10x to the 6th plus 27x to the 5th minus 57x cubed minus 30x squared plus 29x plus 20. Our goal is to solve for the zeros using a provided factorization. Then read the roots from those factors. Step 1. Identify the polynomial function. We will restate the function clearly so we keep track of what we are solving. Step 2. Factor the polynomial. We use the factorization as provided in the example. Let's visualize the unfactored and factored forms side by side with an arrow. The factored form is r of x equals open parenthesis x plus 1 close parenthesis cubed times open parenthesis x minus 1 close parenthesis squared times open parenthesis x plus 5 close parenthesis times open parenthesis x plus 4 close parenthesis. Step 3. Find the zeros by setting each factor equal to 0. We will list each factor and solve for x. From x plus 1 cubed equals 0. X plus 1 equals 0, so x equals negative 1. From x minus 1 squared equals 0. X minus 1 equals 0, so x equals 1. From x plus 5 equals 0, so x equals negative 5. From x plus 4 equals 0, so x equals negative 4. To build intuition, let's place the zeros on a number line and mark multiplicities. Here is a number line from negative 6 to 2. We mark x equals negative 5, x equals negative 4, x equals negative 1, and x equals 1. We will show multiplicity with concentric rings, triple rings for x equals negative 1, double rings for x equals 1, and single filled markers for the simple roots at negative 5 and negative 4. Final answer. The zeros of r of x are negative 5, negative 4, negative 1, and 1. Note that negative 1 has multiplicity 3, and 1 has multiplicity 2. Tip: multiplicity greater than 1 means the graph touches or flattens at that root. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.